So these are the master questions for lesson 2 in this chapter. The first of which is from this paper. This is, where is it? May-June 2013, paper 12. And the question is this one over here, question 3. The straight line y equals mx plus 14 is a tangent to the curve y equals 12 over x plus 2 at the point P. Find the value of the constant m and the coordinates of P. Okay, so you have part of the equation of a straight line. You are missing the gradient. You already know the y-intercept. And you know that this line is tangent to this curve at this point P. Okay, so if you want to get the values of both m, the gradient of the tangent, and P, the coordinates of P, then you have to use the two only facts that you know as being true in this particular question, which is, if you differentiate the function, you'll get an expression to all possible gradients. Okay, if you want the gradient to be m, then you equal that to m, and you have one equation. Don't forget, you want two things. You want the value of x that is going to be the coordinate of point P, with which you can then get the coordinate of y. And you want the value of m. So basically, you have two unknowns. So you need what? You need two equations. You already got one, which is, again, differentiate this and equal it to m. And then if this is a tangent to this, by definition, a tangent is a point of intersection, okay? They touch. So if you equal this to this, you'll need to have a result, and this is going to be your second equation. That's what I did over here. Okay, so I differentiated. Here I separated this in y1 and y2 for you to know what I'm talking about. So y1 is the equation for the tangent, y2 is the equation of the curve. So I differentiated y2 to get an expression to all possible gradients. This is it. Okay, so I equal it to m. Okay, and this is going to be my first equation. But I also know that P is a point that is common to y1 and y2, so I equal 1 to the other, and I have my second equation. So I have a set of simultaneous equations. I just plug in this on the second one and solve it for x, and I get the value of x as being 2. Then I'll substitute it on the expression above, and I get my value of m, right? All I'm needing is the corresponding value of y. Don't forget, this is the x coordinate of point P. So substitute 2 on the either one of the equations, and I get the value 8. So I have here everything that I need, the gradient and the point. See, this is almost 5 free points. This might as well. This is from 2012, okay? But again, these questions are all the same. This might as well be a question in your next exam. 5 free points. Look at how much work you have to do. Very little, all right? Next one is November 2009, paper 12, question 10, okay? All these questions are the same, so don't bother because you are doing, don't worry that you are doing, or I'm solving questions that are for a long time ago, because these might be questions in your next exam, all right? So you have this diagram representing a quadratic and a straight line. So you have the line 2y equals x plus 5, the straight line, and the curve x squared minus 4x plus 7, the quadratic, which intersect at points A and B. Find the x coordinates of A and B. So what do you do to solve this? Point of intersection of a curve and a line, you equal one to the other, or use simultaneous equations. Probably it's simpler in this case. And solve for x, and then get those x's to find the corresponding value of y. That's it. Then the equation of the tangent to the curve at B. the equation of the tangent to the curve at P. In order for you to do that, what do? You differentiate the function to get an expression to all possible gradients, substitute on that expression x by the x coordinate of B that by then you will know, and then use the point B itself, whose coordinates you know as well, to get the value of the y-intercept, and you're done. Then, the acute angle in degrees, correct one decimal place between this tangent and the line to y equals x plus 5. This is the only thing that is new. So let me get rid of these questions, just solve them very quickly so we can focus on this one, which is the one that is new. All right, so as I told you, to get the x coordinates of A and B, you just equal one thing to the other. I have written, instead of using simultaneous equations, I actually rewrote the straight line in the form y equals mx plus c, and then I equal this to that, and I solve it. I will have a quadratic, I use factorization, and I get the values of x as being 3/2 and 3. So this one is the x coordinate of A, is the smallest. This is the x coordinate of B. To get the values of y, substituted. Oh, they just ask the x coordinates, right? Or the full coordinates? No, the x coordinates, so it's done. Okay, it ends here. Now the coordinates of B, you will need to get that to get the equation of the straight line. Substitute 3. Again, 3 is the x coordinate of B, don't forget. So substitute 3 on one of the equations. I did it on the top one, or did I? Yes, I did. And I got the value of 4. So the coordinates of point P is 3, 4. All right. And differentiate the quadratic to get the expression of all possible gradients. Now substitute x by 3. That's the point that you want to get the gradient of, and you have 2. To get the value of c, use 0.34, and you get the value of c as -2. So here you have the equation of the tangent on point P. Then the gradient, the angle between, let's look at it again. The angle between the tangent that you just did and this line. Don't forget, you got here a straight line, the tangent at point P, and this one. So you want this angle over here. How do you get that? I'm going to use this line that is already drawn to explain what gradients have to do with angles. And I'm going to use a line here that is parallel to the x-axis, okay? And a line that is perpendicular to the x-axis. All right? Think of the gradient between the gradient of this line over here. How do you get it? You get it through this point over here, any 2 points, and in this case I picked this one and this one over here, right? So is the change of the y coordinates of these 2 points over the change in the x coordinates of those 2 points. So basically this distance divided by that distance. But if you look closely, you have here a rectangle triangle, right? So what is basically this side over that side on the rectangle triangle? The opposite side over the adjacent side to this angle over here is the tangent, right? This over this is a tangent of this angle. So in another words, the gradient of a line is the tangent of the angle that that line makes with the horizontal, or if you prefer, with the x-axis. So if you get the gradient of this line, you automatically are able to calculate the angle that the line makes with the x-axis. And if you do the same with the line that is parallel, that is tangent to the curve, you will also have another angle. To get the angle between these two, let me just draw here another one for you to understand what I'm saying. So let's say that this line over here is the tangent at that point. Let me just shift it over here. Doesn't want to go there, but I'll force it. All right. Let's imagine that this is the tangent at that point over there. The gradient or the angle that they are asking for is this angle over here, right? So all you need to get is this angle. Now move this further, move this further. Got that angle. And this over here is going to be the biggest angle minus the smallest angle. Make sense? That's what I did over here. The gradient of a line is the tangent of the angle that line makes with the x-axis. So for the tangent of y1 again is the curve. On point P, the tangent of that angle is going to be equal to the gradient, right? Which means that the angle itself is tan minus 1 of the gradient, which was 2, as we saw before, right? Here you have. So the angle is 63.43. I'm putting 2 decimal places because this is an intermediate calculation. And for any angle, the final result should be always correct to 1 decimal place. I think the question itself tells you that, yes, 1 decimal place. So for any intermediate calculation, use 2. Use 2. Otherwise, your final answer should be or could be a rounding of a rounding. In this case, you are safeguarded. Do the same thing for line y2, which is this one over here. Okay, you know the gradient just by looking at the expression is 1/2. So the angle is tan negative 1 of 1/2, which is 26.57. So the angle between them is going to be this one minus that one, which corrected to 1 decimal place is 36.9 degrees. Finally, determine the set of values of k for which the straight line, does not intersect the curve, the parabola. All right. If you look at this, let me take all this stuff out of here. If you look at the equation that you are given, this is basically a line that is parallel to this one over here, right? It's just the y-intercept that is not defined, is in terms of k, okay? So what is this being asked? What is the set of values of k for which this imaginary line that is parallel to this one over here, drawn, does not intersect the curve? It does not intersect the curve if you have a line that is, let me do it over here. Okay. All these lines over here will intersect the curve, right? I'm going to move it, make it bigger, right? So these lines, look, I'm changing the value of k, the y-intercept. Actually, k/2 is the y-intercept, but you get my point. All of these will intersect the curve in 2 points. 2 points, 2 points, 2 points, 2 points, 2 points, A and B. And over here is just going to be 1 point. And this is going to be the limit. If you move this line down, it will no longer intersect the quadratic. So this is the threshold point, starting from which the line will not intersect the quadratic. Okay? So that's what we need to get. I wrote the equation of this line as y equals mx plus c. I equal it to the quadratic to get any points of intersection. And then I have a quadratic that is expressed in terms of k. And if I want, this is the key part, if I want the line not to intersect with the quadratic, then, as I mentioned before several times, you need to set this up, this equation. The discriminant needs to be smaller than 0. In other words, b squared minus 4ac of this quadratic needs to be negative, right? What is your b? B is minus 9. What is your a? A is 2. What is your c? C is 14 minus k. Plug all of these over here and solve it. And then you have k is smaller than 3.875. So for any value of k that is smaller than that, the line will not intersect the quadratic. Okay? This question is always the same. You can standardize this particular question to any other that involves discriminants. The variation is either does not intersect the curve, intersects only once, or intersects twice. And the change would be the discriminant is smaller than 0, is negative, like in this case, equals to 0 when it intersects just once, or is positive if it intersects twice. Last one is this question over here, 8. The equation of a curve is y equals 5 minus 8 over x. Show that the equation of the normal to the curve at a point 2, 1 is this. Again, more of the same. You want the equation of the normal. So what do? You differentiate this to get the expression for all possible gradients. Substitute x by 2 on that expression to get the gradient of the tangent. Do minus 1 over that answer to get the gradient of the normal. And use point P to 1 to get the y-intercept of that line. And that's your final answer. So the equation to the normal of the curve on point P to 1 is this. You have to prove. So the gradients of tangents to the curve, you get them by differentiating the original curve. This is it. Now substitute x by 2 to get the gradient of the tangent, not the normal, of the tangent on this point. The gradient of the tangent is 2. So the gradient of the normal is minus 1 over 2. So you're halfway through. You need to get the value of c. Use that point, and you get the value of c as 2. So this is going to be in the form y equals mx plus c, the equation of the curve, but they want in that form. So get rid of the denominator and organize things so you get the 2y plus x equals 4. Now question, it continues. This normal meets the curve again at point Q. Find the coordinates of Q. Again, we are being asked to get points of intersection of a line and a curve. You already know the coordinates of both. So in this case, I used simultaneous equations to get the coordinates. What did I do here? I solved this in terms of x, plug this over here, then got the same denominators as 4 minus 2y. Okay. Eventually, I have a quadratic, which I can factorize, and I got the values of y first, and then substituted there to get the values of x. Obviously, one of the points is the point that you already know, is the 2, 1, okay? And the other one is the one you are looking for. And last question, find the length of PQ, okay? You know the coordinates of P, you know the coordinates of Q, just need to use the equation of distance between 2 points to get the distance, 11.2 units.